Hey guys, welcome to day 11 of programming every single day until I graduate college. I had another day of school, and I think today pretty short. I'm gonna keep it simple because I'm pretty tired. I probably want to finish this up pretty soon, but it's a lot of content. Chapter 8 is a lot. So probably for the next few days I might just go over this. Maybe today I'll go through 3 and 4, maybe 5 if I have the energy for it, but depends on how these work. Let's see what else is there. Types. Yeah, let's just get through 2 to 3 chapters today. And then maybe tomorrow I'll think of some other. I'm gonna think of some projects to maybe have closed slowly along the semester and stuff. So, anyways, let's just read into it. Alright, so last time we talked about kind of the intro to like functional languages, right? And a bunch of list comprehensions, Texas ranges. Yeah, these are cool, pretty nice. The dot spread operator looks pretty nice. So pretty nice stuff, but the types, we're gonna learn some types in some of these joints here. Let's see how long this is. Maybe I'll only get to one. I don't know. These are a lot of reads. So types and type classes. Believe the type. Previously we mentioned that Haskell has a static type system. The type of every expression is known at compile time, which leads to safer code. If you write a program where you try to divide a Boolean type with some number, it won't even compile. That's a good thing because it's better to catch such errors at compile time instead of having your program crash. Everything in Haskell has a type, so the compiler can reason quite a lot about your program before compiling. Unlike Java or Pascal, Haskell has type inference. If we write a number, we don't have to tell we don't have to tell Haskell it's a number. It can infer that on its own, so we don't have to explicitly write out the types of our functions and expressions to get things done. We cover some of the basics of Haskell with only a very superficial glance at types. However, understand that types is a very important part of learning Haskell. A type is a kind of label that has every expression has. It tells us which category of things that expression fits. The expression true is a boolean, hello is a string, and etc. Now we will use the GH CI to examine the types of expressions. We'll do that using the :t command followed by any valid expression tells its type. Let's give it a whirl. So type of that should be character. Interesting. Type of that is Boolean. Type of this is a character. Array of characters. And this is type of a Boolean character. And it's a Boolean. Oh, this evaluates. Here we see that the :t, the command T on an expression prints out the expression followed by the ::, and its type is read as has type of. Explicit types are denoted with the first letter in capital case A, as it would seem, has a type of character. It's not hard to conclude that the stands for character. True is of a bool type. That makes sense. But what is this? Examine the type of hello. Yields a character. The square bar denotes a list, so we read them as it being a list of characters. Unlike list, tuple length has its own type, so the expression true has a type of bool character, as an expression such as ABC would have a type of character, and 4 equals 5 will overturn false, so it's a type Boolean. also have types. When writing our own function, we can choose to give them an explicit type declaration. This is generally considered to be good practice, except when writing very short functions from here on. We'll give all the functions that we make type declarations. Remember the list comprehension we made previously that filters the string so that only caps remain. Here's how it looks like with type declaration. Remove non-uppercase. As a type character, meaning that it maps from a string to a string. That is because it takes one string as a parameter and returns another as a result. The character type is synonymous with string, so it's clear if we write remove non-uppercase. We didn't have to give this function a type declaration because the compiler can infer by itself is a function from a string to a string, but we did anyways. But how do we write out the type of a function that takes several parameters? Here's a simple function that takes integers and adds them together. The parameters separated with, and there's no special distinction, the arrow symbol, and there's no special distinction between parameters and the return type. Type is the last item in the declaration, and the parameters are the first three. Later on, we'll see why we'll just separate it with this instead of having some more explicit distinction between return types and the parameters like int, something. If you want to give your function a type declaration, but unsure as to what it should be, you can just write your function without it and then check it with the type command. Functions are expressions, so the :t works without them. There's an overview of some common types. Int stands for integer. It used for whole numbers. 7 can be an int, but 7.2 cannot. Int is bounded, which means that it has a minimum and maximum value. Usually a 32-bit machine, the maximum possible int is, well, like, what is that, 200, or is that 2 billion? I think so, yeah, 2 billion. This is 100 million, and the minimum is negative 200 billion, right? 2 billion. Integer stands for ER, also integer. The bounded, so it can be represented. So int and integers are different. Pretty nice. Float is a real floating point with single precision. Double is a real floating point with double the precision. Alright, pretty nice. Boolean is a Boolean type. We can only have two values, true and false. Character represents a count, is denoted by single quotes. A list of characters is a string. Tuples are types, but they're dependent on their length as well as their types of their component. So tuples are types, but they're dependent on their length as well as the types of their components. So theoretically, an infinite number of tuple types, which is too many to cover in this tutorial. Note that the empty tuple is also a type which can have a single value. Type variables. What do you think is the type of the head function? Because head takes a list of any type and returns the first element. So what could it be? Let's check. Well, head returns, what was it? Yeah, first element. What is this? A? We previously stated that types are written in capital case. So it exactly can't be a type, but it's not in capital case. It's actually a type variable. That means that A can be any type. This is more like generics in other languages. Only in Haskell it's much more powerful because it allows us to easily write general functions if they don't use any specific behavior of the types. Functions that type variables are called polymorphic functions. Functions that have type variables are polymorphic functions. The type declaration of a head that it takes a list of any type and returns the one element of that type. Although type variables can names longer than one character, we usually give them names of A, B, C, D. Remember FST, it returns the first component of a pair. Let's examine its type. Although type variables can have longer names. Okay. We see that FST takes a tuple. That's why we see that FST first takes a tuple which contains two types and returns an element which is the same type as the pairs component, first component. That's why we can use FST on a pair that contains any two types. Note that just because A and B are different type variables, they don't have to be different types. It just states that the first component's type and the return values types are the same. Type classes. Type classes is sort of an interface that defines some behavior. If a type is a part of a type class, that means that it supports and implements the behavior of that type class describes. A lot of people coming from OOP gets confused by type classes because they're thinking like classes in object-oriented language. Well, they're not. You can think of them as Java interfaces, only better. What's the type signature of this equality function? So this guy definitely hates Java or something. The type of this equality is a function. So are these operations, pretty much all operators. If a function is comprised only of special character, it's considered an infix function by default. If we want to examine its type, pass it into another function or call it a prefix function. So we surround it in parentheses. So I'm curious on that's an interesting that's a very interesting so this is giving us what the type is. Interesting. And we see a new thing here, the arrow function. Everything before the arrow function is called a class constraint. We can read the previous type declaration like this. The equality function takes two values that are the same type and returns a bool. The type of those values must be a member of the equal class. Okay. This was the class constraint. We can read the previous type declaration like this. The equality function takes any two values that are the same type and returns a bool. We can read the previous type declaration like this. The equality function takes any two values that are the same type and returns a bool. It must be a member of the EQ class. This was a class constraint. Okay, so that's what the arrow function is. Okay. The EQ class, type class, provides an interface for testing for equality. Any type where it makes sense to test for equality between two values of the type should be a member of the EQ class. All standard Haskell types for I/O. The type for dealing with input and output and functions are part of the EQ type class. The element function has a type A and returns A in a list. Bool, because it uses to check whether some value we're looking is in it. True. Some basic type classes. EQ is used for types that support quality testing. The functions it members implements are equals and the does not. If there's an equal EQ class constraint for type variable in a function, it uses equals or does not somewhere inside its definition. All types previously mentioned except for functions are part of equals, so they can be tested for equality. All the types mentioned previously before are part of equals, so they can be tested for equality. Is used for types that support equality or okay. Ord is for types that have ordering. So we have EQ, that's a type class. And all the types we covered so far except for functions are part of the ord. Ord covers all the standard functions such as the compare function between two ord members of the same type takes two ord members of the same type and returns an ordering. Ordering is a type that can be less than, or was it greater than, less than, or equal, meaning greater than, less than, or equal respectively. To be a member of ord, a type must have a membership in the prestigious and exclusive equality chrome. That is true, because it's, yeah. I'm curious of what this mean. Like, does it output a string like LT? So like if I say 5 compare and if I say this is GT. Okay, so it is. Oh wait, it's just variables or something. Okay, they're like keywords, I think. Members of show can be represented as strings. All types can are part of the show. The most used function that deals with the show type class is show. It takes a value whose type is a member of show and presents us to initiate. Okay. Read is sort of the opposite type class of show. The read function takes a string and returns a type which is a member of read. Read true. string and returns a type which is the member. Okay. Here, so if I say read, here's another function, read. Interesting. Or what was the read for? So far, so good. Again, all types covered so far in the type class. But what happens if we try to just read for? What GHCI is telling us here is it doesn't know where we want in return. Notice that in the previous uses of read, we did something with the result afterwards. It doesn't. So what GHCI is telling us here is that it doesn't know what we want in return. Notice that in the previous uses of it, we did something with the result afterwards. That way, GC can infer what kind of result we wanted out of our read. If we used it as a boolean, it knew it had to return a boolean. But now it wants some type that is a part of the read class. It doesn't know which one. Let's take another. Takes a string and see it returns a type that's a part of read. But if we don't try to use it, did he say that everything in read but if we don't try to use it in some way, it has no way of knowing which type. That's why we can explicit type notes. The type annotations are a way of explicitly saying what the type of an expression should be. The type annotations are explicitly. That's why we use explicit type. The type annotations are a way of explicitly saying what the type of an expression should be. We do by adding and specifying a type. Observe. Very nice. Kind of a conversion here, like typecast. Read. Integer. Float. List. What is it? Array then? Is there a list type? I guess that's not. Oh, you have to. I see. So you have to specify. I don't know, like the type you want. Oh, you can't. The frick. That's kind of cool though. Wait, I can't put float here. Why not? Oh, I'm just doing it wrong. What am I doing wrong? It has to be the same type. Ah, gotcha. So I have to. This has to be a type of. I don't know if this, like, I have to do this. It has to be a string, then it works. And if what if I say, I don't know, a string. I don't know if that works. Or char. Or float. So I guess it has to be the type, like this is the way to do it. Expressions are such that the compiler can infer what the type is by itself. But sometimes the compiler doesn't know whether to return a value of type int or float for an expression like read 5. See what type of Haskell has to evaluate read 5, but since Haskell is statically typed, it has to know all the types before the code is compiled. So we have to tell Haskell, hey, this expression should have this type in case you don't know. Enum members are sequentially ordered types. They can be enumerated. The main advantage of enum type classes is that we can use it in types in list ranges. They also have defined successors and predecessors, which you can get with the suc and pred functions. Types in this class is boolean, tuples, characters, ordering, and integer, float, and double. This is very interesting. That one's cool. The LT to GT. Okay, I don't know why that don't work. They have to like that. Oh wow. Less than, equal, greater than. What's the pred of? Oh, it's the @ symbol. Really interesting. Okay, it's like ASCII value. So it doesn't loop back, but okay. Predecessor of this. Okay. This is mostly some kind of ASCII value. Could that be even possible? No. Well, these are not a character. So I don't know if predecessor exists for some other things. So yeah, enums. Bounded members have an upper and lower bound. Min bound. Min bound and max bounds are interesting because they have the type of bounded A. What does the arrow do again? I forget. Oh, the class constraint. Okay. The class constraint is bounded. In a sense, they are polymorphic constraints. What is polymorphic? Polymorphic. Okay. So polymorphic. Min bound and max bounds are interesting because they have a type of bounded A. They're polymorphic constraints, so they have types. All tuples are part of bounded if the components are also in it. Num is a numerical type class. Numeric type class. Its members have the property of being able to act like numbers. Let's examine the type of a number. It appears that the whole numbers are also polymorphic. The whole numbers are polymorphic constants. They can act like any type that's a member of num type class. They can act like any type that's a member of num type class. I get confused on what this does. What is the notation for this again? Oh, it's just type of notation. So if it just has type of. Okay, so we're saying 20 has type of integer, integer, float, double. Those types are in the num type class. If we examine the type of this, we see it accepts all numbers. It takes two types of the same numbers of the same type and returns a number of that type. That's why will result in a type error, whereas will work just fine and produces an integer because 5 can act like an integer or int. To join num, a type must be friends with show and eq. Integral is also a numerical type. Num includes all numbers, including real numbers, integral numbers. Okay. Floating includes only floating point numbers, so float and double. A very useful function for dealing with numbers is from integral. It has a type declaration of from integral from its type signature, so we see that it takes a integral and turns it into a more general number. That's useful. The integral, floating point, integral and floating point types to work together nicely. For instance, the length function has a type declaration of this. I think there's more historical reasons of something, although in my opinion it's pretty stupid. All right. Where am I? That was type 3, chapter 3, so. Syntax functions. All right. I think that's enough for today. I was hoping to 2 to 3, but these are long reads, so maybe I'll do some reading on my own time to show more programming, as I didn't program that much, but long day, so I gotta make a video somehow. So we're almost there. We got at least halfway there. I gotta read this, and then hopefully I can think of a project by tomorrow, because I think I have some ideas, but we'll see. But anyways, thanks for watching. We'll see you for tomorrow's video.